Mei Yin, and she will talk about sparse graph limits.
Thank you very much for the organizers to put up together such a wonderful workshop. I literally enjoyed every moment of it, and part of me wished that the workshop could be longer. It's a real pity that Sophia could not make it. She and I were flatmates during a long workshop at the Newton Institute in Cambridge many years ago, and she taught me how to speak like a real mathematician. For example, instead of saying, I haven't made up my mind yet, a better way to put that would be, my mind hasn't converged yet. There are many such fun stories from her. So I've been working on dense random graphs for more than 10 years and have made friends and met collaborators along the way. Coincidentally, the first conference talk I gave on this subject was at Your Random in 2011. And I remember Remco was a scientific director. And after my talk, he asked me, so do you have any results for sparse graphs? Yeah, so embarrassingly at that moment, my understanding of sparse graphs was very naive. And my sparsest result was an ergon model outputting a graph whose edge density goes to 0, but it's still in the n square limit. Remco, you might not know this, but your question stuck with me ever since. And today I'm going to give my first conference talk on sparse graphs. It's a continuing learning process for me, and I'm excited to share with people what I've known so far. So before sparse graphs, there is dense graphs. So I'm going to summarize the dense graph theory in a couple slides. So like starting point for learning about all those graph models, I would say Lova's book on large graphs, and also Remco's 2-volume book. One was already published. I didn't put 2022 plus, because I saw on your website, you said it's 2023, and I believe. Yeah, okay. And then, sure. So for graph on space, we've seen many times by now. It's a function from the unit square to the unit interval. And then the function value denotes the probability of putting an edge between the two vertices. So people have studied this dense graph theory from different perspectives. And then there are different ways to characterize convergence. There is left convergence, right convergence, metric convergence, convergence of quotients, etc. In particular, left convergence and cut metric convergence are more or less the same. And then the other convergence are also equivalent under the condition of compactness. So you might remember that for classical dense graph regime, the function is from the unit square to the unit interval. There is nothing special about this being a unit square, except that it's compact. So under this compactness regime, there are lots of nice results showing convergence and low LDP. And then, yeah, over the years, people have had many results. And Chatterjee and Diaconis were among the first people to put a rigorous theory on dense graph limits in ergon. And then in the audience, Brendan Hollander and Charles Reardon also had a number of papers from the statistical physics perspective. And then in the statistics, so yeah, this is just like a picture showing the view of dense graph limits. And then in the statistics community, people have studied limiting graphs from a variety of perspectives. And many people here in audience are experts at all this convergence result and also application, simulation, and many things. So I will first give a survey on the sparse graph limits, and my survey will mainly be based on the results in Wittgenstein and also in Boltz, Chase, Kohn, and Holder. Okay, so to go from sparse graph, dense graphs to sparse graph, there are different approaches you can take. So the approach I'm going to talk about today is going from array to measure. So as have been mentioned in the past days, for dense graphs, the theory relies on the exchangeability result from Aldous and Hoover in the 1979 through 1981. And then at that time, when we are talking about exchangeability, it's for arrays. But if we extend it to more generally to measures, there is Kallenberg's representation theorem. And then I'm going to expand on that in the next few slides, but also please let me note that the sparse graph limit theory in this setting will cover a wide class of sparse graphs, but also not all possible sparse graphs. For example, the Barabasi-Albert preferential attachment model, and also the model discussed by Lutz on Wednesday, are not covered under this theory because we do need a certain sense of exchangeability for the theory to work. Okay, so this is Kallenberg's representation theorem in a nutshell. So for graph form, we just have a function from the unit square to the unit interval. And then more generally, there is something called the graph fix. The graph fix has three components. One is a graphon component, and one is a star component, and one is the dust component. And the dust component consists of isolated edges, but still the graphics component is a major component. And the idea is that instead of restricting ourselves from the unit square to the unit interval, we can do from r plus square to the unit interval, or even more generally from r plus square to r. And then the s part, the star part, will be an integrable function. And then the dust part will consist of isolated edges. So all these three components will be driven by independent Poisson processes. And for typical realization, we can take S equals W equals 0, and then still just think about the graphics part. And also, we can generalize even more from r plus squared even further to sigma finite measure space, and the result will follow through. So how do we visualize this when we are given a graphics W? The idea is that we will first run a Poissonization argument, and then we put points down on r plus square, and the points will follow. Typically, there will be infinitely many points there, and then we connect the points theta I comma theta j with probability w comma mu I mu j, and then S and I, should they be non-zero, would respectively correspond to the star and isolated edges, like I just mentioned. And then to model a growing graph, typically people would also do some time cut and then let the model grow over time. So this is a super simple illustration of what is going on. So the idea is that we would put down points following a unit rate Poisson process. So here I just put down 2 points, but in general, there'll be many, many points. And then say I look at this point and this point, I would connect the theta values of these 2 points. So this point and this point become this point and this point here. I will connect the theta values of these points by their corresponding value in W of mu I, mu j. So we see that here the mu I value is equal to this, and the mu j value is equal to this. And again, this is just a simple illustration of what is going on. In general, like you will, if you do a time cut, then you will have infinitely many vertices and finitely many connected edges in the space. So the main takeaway for the sparse graph limit theory is that when we do not have compact support, many interesting phenomena could happen. And then also, when we have compact support, then the different, like the different vertices, given those variables, they are independent, but now the latent variables associated with the vertex are not independent anymore once the support is not compact. And so the space of probability distributions on dense graph can be parameterized by graphons, and then the space of probability distribution of sparse graph can be parameterized by graph fixes. And thank you to Peter Robbins for a very informative talk on Tuesday and help clarifying a lot of confusing points on ergodic theory. So for the graph dense graphon space, the extremal points are precise. They are the extremal points of that ergodic theory. And then for sparse graphs, the graph fixes are precisely the extremal points. And all other probability measures will become a mixture of those. All right, so
I just want to make sure I understand the definition. So for an example, suppose I construct a random geometric graph in the following way. So I'm going to reveal a larger and larger region around the origin in R2, say, or R if you prefer. And then I have points that are generated by a Poisson process with some fixed density. And then I connect 2 points if the distance between them is lesser than or equal to 1. So some people call this the unit disk model.
Yeah.
And so as it grows, you know, everybody has a constant average degree and so on. So is this a graphics where the function W is sort of large on the diagonal, where, you know, we connect things if they're, you know, it's one within a certain band, because that's how, if they're, and zero outside that, or is this not a graphics, or?
I mean, typically for dense graphs, for dense graphons, the convention is to take the diagonal to be 0. And then for graph fixes, like the convention is to take the diagonal to be 0, but there are definitely generalizations. So as long as it's a function from r plus square to 0, 1, that's considered to be a graph fixes. But like, depending on what W looks like, there will be different properties derived.
Okay, well, I guess I got W wrong. I mean,
No, you got it right. I think your W is defined on, let's say, just
I think you got it right. So if you actually would do, you can think sort of, let's say it's on R. Okay, then you can think of the position in R as a feature, and 2 vertices in W is a function on R cross R, and it's non-zero around the diagonal. Maybe at the diagonal it's 0, but then in a band of width, your radius, it's non-zero. And that would be an example which fits her stuff.
And if I want to do this on R2, I have to do the usual crazy
Yes.
continuous map from
Or
R.
you can do it on R2 too.
Thank you.
But it's not integrable, so it doesn't fit into this theory, right? Because the diagonal extends to infinity.
That's a very good question. I'm going to talk about, right.
Okay.
So in Christian's paper, they assumed the graphics to be integrable, but later today we will see that we can extend the theory in some sense. All right, so for graphics or like just the graphon part of the graphics, there are different notions of metric. There is that cut metric for dense graphs. And then because right now we are talking about sparse graphs, so there are potentially different ways to generalize a metric. One is called the rescaled cut metric, while you rescale the height of the function. And there is also stretch cut metric, where you stretch the domain of the function. And also there are many other metrics. So I'm going to show a picture illustration of what's going on. So this is a graphon, and in the cut metric, the standard cut metric, and this is the rescaled cut metric, while I'm going to just stretch the height of the function. And there is also stretch metric, where I'm stretching the domain of the function. Okay.
But are you assuming that the domain remains compact?
So it's just a picture illustration. So like my domain will not be compact. I'm just showing like to consider. All right, so I'm particularly interested in the rescaled and stretched cut metric because of the example I'm going to present today. And we are going to see that under certain conditions, it will be rescaled metric. And then if we change the model a bit, suddenly we are in the stretched cut metric regime. Okay.
But for the cut metric,
Yeah.
if your space is non-compact, all right?
Right. So we are just talking about dense graph. I'm saying that this is
okay.
a standard metric. Okay. I felt like so far I've been borrowing from Christian and various people's work till now. So now finally I'm going to tell you something about my own work. Okay. So I'm going to use a toy example to showcase various interesting things about sparse graphs. And we will cast it in the graphon limit theory framework and also see some other interesting phenomena. So I got into this model from reading a paper from Christian, and there he presented a motivating example for a power law graph to study LP graph convergence. And I was like, okay, this model is interesting. What if we twist the model a bit? What will we get? So let's first look at their model. The model is that if we have n vertices numbered 1 through n, and then we connect the vertices ij with this probability. So essentially what we are doing is that we connect the different vertex labels, I mean ij, with connection probability ij to the power -1 over alpha. And then we are going to boost it by a factor of n to the beta in case the connection probability becomes too small. And sorry, I should also mention that they studied this model in the parameter regime where alpha is greater than 1 and beta is in between 0 and 2 over alpha.
It means that the average degree grows like a positive power of n, right?
Exactly. So the average degree for their model, I think I wrote it somewhere, right? So it grows like n to, the edge density grows like this, and the average degree grows like to the power -1/alpha. And then they found out that in the rescaled cut metric, the limiting graphon looks like this. And then this limiting graphon is in LP for any p less than alpha. So this is their model. And I was thinking, okay, what if we change the model a little bit? So we still have n vertices numbered 1 through n, and then we connect the vertices ij with this probability. Okay. So you can see that right now it's a deterministic probability, not the probability they have here. So their probability is like, if this value is greater than 1, definitely deterministically we connect the two vertices. If the value is less than 1, then we connect it with certain probability, less than 1. So there's some randomness there. And then for my model here, it's like if the product here is greater than 1, we still connect them. And if the product is less than 1, we just don't connect them at all. So our graph will be sparser than their graph. And their graph is already sparse. So this graph will be even sparser. And then I also reformulated the notations a little bit, but you can see the resemblance here. So I will still have a normalization constant here. And then you might remember in their model, it's I over n to this power and j over n to this power. So instead of having I over n and j over n, I just say it's an IID uniform 0-1 random variable. So I continualized the setting a bit, and then still power -1/alpha. But the major difference is that I dropped all those so-called soft edges. Right. So for this model, and also I should mention that for their model, the parameter regime they are interested in is in this parameter regime. For the adapted model, I will study the model in every parameter regime. So in particular, there is a so-called critical regime, and this critical regime can be reformulated as a personalization point process convergence, and it was studied in this paper. So actually, they studied parameter very large, but then under some formulation, it can become parameter very small. And then in this talk, I'm going to concentrate on the model away from criticality. As we will soon see, there will be a subcritical regime and supercritical regime. And the supercritical regime will correspond to the parameter regime in Christian's paper. So, and here I just wrote down more explicitly of what happened between their model and my model. So the first thing is that we did a continualization of the vertex labels. That's of minor technicality. And the major thing is that we dropped many more edges. And also like for the parameter regime they studied in our paper, in their paper, it would become the supercritical regime. So beta greater than 0 will become an less than n to the power 2/alpha. And the interesting thing is that by dropping all those edges, suddenly the limiting graph will become convergence in the stretched cut metric instead of rescaled cut metric. Okay, and then I felt like here I'm borrowing some terminology from statistical physics. I don't know how accurate they are, but I'm saying that if the edges will definitely be connected, I will call them hard edges. If they will be connected with certain probability less than 1, I will call them Bernoulli edges, because whether I connect them or not, they follow a Bernoulli sampling probability. And then again, for Christian's model, it has both hard edges and Bernoulli edges. And for this adapted model, it will only have Bernoulli edges. Oh, sorry, it will only have hard edges. And then I also made another parameter transformation for an to the alpha. I now named it n to the gamma log n. So the log n parameter here is mainly for technical convenience. We can drop it. It will not affect the argument. So then gamma greater than or equal to 2 and gamma less than 2 will correspond to the different regimes. Or you can just say gamma greater than 2 will become the subcritical, and the gamma less than 2 will become the supercritical. And then the critical regime was well studied. Its an varies as n to the power 2 over alpha. And we will show that like in the different parameter regimes, we see different phenomena. And when it's in the subcritical regime, usually we will not see any graph. It's always empty. And in the rare case that it's non-empty, we will see exactly one edge. And then contrarily, in the supercritical regime, we will see a limiting graphon emerging in the stretch cut metric. And also we will see that the parameter alpha mysteriously disappears. So there is some universality under certain rescaling. All right, so first the simulation picture. So this simulation picture was done for different values of alpha and gamma, and also for n equals 10,000. Okay. And then one thing I wanted to note is that, so here I ordered the vertices from according to their degree. So here it's a degree from large to small. And we can see that this is like, this curve shows the degree distribution in some sense. And then for larger degree to smaller degree, this seems to be like 1 over x tendency. And we will justify that in a minute. And to study this model, I group the different vertices into 2 types of vertices, one called clique vertex, the other called follower vertex. In some sense, this goes back to Shiver's type 1, type 2, and all these different types. Okay, so for clique vertices, I just separate them by the value xi greater than the square root of an, and the follower vertices are less than or equal to that. So in other words, all clique vertices will definitely connect, and the follower vertices will only get connected to a clique vertex, but not among themselves. And this is a picture showing what I mean here. So these are the clique vertices, and these are the follower vertices. Okay, just a simple illustration, right? And then there are some straightforward calculations we can do. So expected value of the number of edges will scale like this. And then expected value of number of vertices will scale like this. So because this is like a toy example, so all these computations can be done rather easily. And then in the subcritical regime, because we can study the clique vertex number, and then it varies as a binomial distribution with this parameter. And we can check that the number of clique vertices greater than or equal to 1, the probability is the same as the probability equal to 1. And then it scales like this. And then it's always going down to 0. So only conditional limit theorem is worth studying here. And there is a fine point here, because just that we have a clique vertex does not exactly mean it's a clique vertex. So it could be that the follower vertices do not get connected to the clique vertices. So in fact, the probability that we have a clique vertex and the follower vertex gets connected to the clique vertex is smaller than just having a clique vertex. But then having exactly one follower vertex has the same probability as having many follower vertices. And also notice that here we can only have follower vertices for this one particular clique vertex. We can have we cannot say have different classes of follower vertices because there is only one clit vertex. And then, so in the typical regime, we will have exactly 2 vertices and 1 clit vertex and 1 follower vertex. So I tried to find a physical intuition for that. Again, like Charles and Frank are probably better experts at answering these questions. But like the interpretation I had in mind was that there's some energy pushing follower vertices to clit vertices and other vertices to follower vertices to get connected to things in the graph. And then we only have certain energy to do that in the subcritical regime. So this is the best we could do. All right, so now let's finally move to this more exciting supercritical regime. So to study the phenomena in the supercritical regime, it's more technical. So what I did was that, so for each vertex, I will consider the number of vertices connected to that vertex, and this will give me a height function. So I will only consider the height function for the vertices in the clit. And then for 0 less than x less than or equal to 1, this denotes the number of vertices that are connected to the top xk and 0 clit vertices. So k and 0 represents the total number of clit vertices. And by varying x from 0 to 1, it tells me exactly how many vertices are connected to the clit vertices. And then it will give me a curve. So in particular, Hn of 1 is the number of followers of the leader from the clit, and Hn of 0 is 0 by convention. So Hn of 1 is the number of followers of the leader because Hn of 1 means the clit vertex with the largest value. So if it's a clit vertex with the largest value, then if a follower vertex will get connected to other clit vertex, it will get connected to this leader. So this is an increasing function. And then the main theorem is a Brownian motion convergence result. So showing this. So let me first talk about some implications of this theorem before we look at the details. So actually to derive this theorem, the first thing I did was I calculated the expected value of this Hn of x and also the variance of Hn of x. And I found that they both scale according to the same scaling limit. And then I was like, okay, more things can be said here. So in some sense, when we consider graph limit theory, we say that in the limit, the graph converges to a limiting graphon. That's like a first order approximation. So here, if we subtract the value, the average value from the actual value, because it's a random variable, there are some still higher order fluctuations over there. And this higher order fluctuation is captured by this Brownian motion thing. Okay. And then when I got this result, I thought it's already pretty good because I've never seen such degree fluctuation results anywhere else. And I talked with Svante, and he was like, oh, you just need to make some twists here and there, and then you can go from FDD convergence to process convergence in the Eurostar topology in your space D of 0, 1. So there are stronger results we can say here. So before diving into the proofs, what's the main implication here? So from this FDD convergence, we can see that in the limit, expected value of this height function varies like this. And then the variance of the height function has the same scaling, and then also an explicit formula like this. And then because I'm ordering the clit vertices with their value from small to large, it introduces a simple transformation from the simulation picture I showed you earlier. So it's a simple transformation from x going to 1 minus x. So from here, we can get the boundary curve we saw earlier would be 1 plus this divided out by the scaling thing. And it's exactly 1 over x, like we saw in the simulations. And this 1 plus is because for this hn of x height function, you might remember we just denote this to be the number of follower vertices that are connected to the clique vertices. So all the clique vertices are connected to themselves. So there is an actual 1 plus thing here. And then the scaling I used here is also by this expected value of the number of cliques. And it will be more apparent in a few minutes why I use this scaling. So, okay, so further implications. Okay, so you can see that essentially this result is saying that under this expected value of number of clique scaling, we will get a limiting graph form, and the limiting graph form will be random free. It's x1 less than or equal to 1 is 1, and then otherwise it's 0. So this feels very similar to the stretched cut metric convergence we talked about earlier. For the stretched cut metric convergence, it should be stretching by the 1 norm of this Wn, and it's equal to this. And here, if we have the log n factor, it has an extra log n factor. So if we drop that log n factor, it's exactly the stretched cut metric convergence. And if we keep that, it's still very similar, but then more or less on the boundary of that convergence. All right, so for the last few minutes, let me talk about the proof for this. So the idea of the proof is that we are going to introduce IID sequences of random variables. So one is according to whether they are clique vertices or follower vertices. We do them according to whether the value is, I name them different numbers, y and z, and then the y vertices are the clique vertices, and then all these. So this part gives me the different thresholds for where the follower vertices will fall between. So by different thresholds, I just mean some follower vertices will get connected to all the clique vertices, and some follower vertices will get connected to, say, only one clique vertex. And then, and then for all the different x values, we introduce this tau n of x, the threshold function, and then by the threshold function, we can rewrite the height function as a sum of these Bernoulli random variables. So, and then we will study the order statistics of this, and then nested Bernoulli random variables. And then the proof is quite technical. It's several pages using convergence of quantile processes from Shorak. So if you're interested in more technical details, happy to tell you more later. Okay. So, and then a bit more details is that, so the proof technique is that we are going to write this BNI of x and then subtract the conditional expected value from that. You might have seen this already in Baswell's talk earlier. Okay, so, and then this part will give us the Brownian motion part, and the difference will give us an independent Brownian bridge part. So, yeah, and also Shiva's talk gave us similar methods. Okay, so lastly, let me give some final remarks on why I find this model interesting. So first of all, this W of XY limiting graph, it's random free. It does not depend on the parameter alpha, and also it's not L1 integrable. So even though Christian's paper studied like all those LP graphons and convergence, this shows that there are more generalized results. So we don't necessarily need to constrain ourselves to LP graphons for the convergence. And also this W of XY, it's however locally finite and satisfy weak convergence results discussed in originally. And then for, so I checked the generic formulas in Roy, and then the theoretical results match pretty well in this setting. So in this setting, I was using Brownian stuff, and then it's very similar results under the scaling in KN0. So in their papers, they named this scaling as mu. And then also certain technical conditions of the model may be relaxed. Here, I'm saying that it's a hard edge model. Well, the vertex labels satisfy a uniform distribution and so on. It feels very special, but then many conditions can be relaxed. For example, we don't necessarily need to consider exponential distribution. It can be a distribution with regularly varying tail, and then the results will still follow. But then more generally, seeing such Brownian motion and also second order fluctuation in the limiting graphon, naturally people would wonder, like, does this hold more generally? And then I talked with Svante, and he told me some intuitive guesses. He said it's not entirely sure about everything, but his intuitive guesses are like, for hard edges, we can extend the situation to more general models. We don't necessarily need to have product exceeding a threshold. It could be sum exceeding a threshold and so on. But if we actually go back to Christian's model, where there are hard edges and ballooning edges, then maybe we will not see such nice Brownian motion in the limit, because the white noise is stronger there. Yeah, but many more questions we're thinking about. And also here, I only discussed the degree distribution. It could be like subgraph density or other things. Yeah. Okay, so I consulted many references while preparing this talk, but these are the main references I used. Thank you.
Okay, so we have time for a few questions.
Are there settings in your model where the average degree converges? And if so, would you be able to prove local convergence?
Oh, that's a very good question. So I mean, like, for the average degree, I mean, like, I know the degree at every vertex, every clique vertex, it's given by this value. So like, you have averaging results, but local convergence, I've never thought about that. That's a very interesting question.
Because the clique vertices are very rare, right? So the followers are going to be the main contribution for the local limit.
Yeah, that's exactly right. So the main number of edges will come from follower vertices getting connected to clique vertices. But clique vertices themselves, yeah, they only contribute a small part.
But I doubt that you're going to have a local limit.
Why?
Well, I mean, she doesn't have bounded average degrees the way it's done, right? Because the integral, so the degree is 1 over x. So the integral of the 1 over x is divergent. If that integral were finite, she would have bounded average degree, but she doesn't. So, which is actually a little related. I mean, as you pointed out, you're sort of at the boundary of the stretched cut metric convergence, and you're sort of also of the boundary of the more general graphics. So there are two versions as not here anymore. No, you observed. As people observed the graphics convergence thing, you can formulate in two settings. One is where the graphics, well, the graphon is integrable. And then there is a version where the graphon is locally finite, as you pointed out, but not necessarily integrable. And they're slightly different. So I wonder whether, and she's just at the boundary of the two of them because her thing is almost integrable. And so I could imagine that you could do some tweaking, trying to sort of forget, well, the cliques will just have unbounded degrees in her setting.
Yeah, so in general, you will not be able to have a local limit when you have followers that are mainly connected to the clique vertices, if the clique, even if you have very few clique vertices, but they have growing degrees, right? Because then the one neighborhood is going to have already vertices that have unbounded degrees.
Yeah.
So then the only way how you can fix this is by having the majority of your followers not having any degree.
Right.
And then you do have a local limit, but it's not very interesting.
Yeah.
Other questions? Okay, well, good. So you get your lunch. Oh, you have a question or you're clapping? Okay, let's thank you again.